Hello everyone, welcome back. If you are new, this is a new series that we have started in which we are trying to decode segment trees from scratch. I already uploaded one video in which I discussed the basics of segment tree, when to use it, how to use it, and we discussed how to build segment trees, how to do point updates and range queries, what are their complexities, everything from scratch. If you are new to segment trees, I would strongly encourage you to watch that video first before coming to this video, because that will be a prerequisite of this particular video. If you know a bit about segment tree, you can directly start with this video. That's fine. Now, in the previous video, I asked you to solve one small practice problem that would help you implement the pseudo codes that we have discussed for all these functions, right? In this and I also mentioned you that we can implement range updates and point queries using point updates and range queries itself. Not always, but in some cases, and I given one practice problem to you which corresponds to this case. And I asked you that we will solve this particular problem with and without lazy propagation in this video. But there's a small change in plan. What I thought is, even these two techniques, point updates and range queries, are very rich. Rich in the sense that you will be able to solve a wide variety of problems with this technique itself. When I say wide variety, you will be able to solve various hard level problems as well. So in this further in the series, we will be solving various code forces level E problem or ICPC hard level problems as well. So stay tuned. In this particular video, the plan is just to give you a code or just to walk you through the code of the practice problem, and we'll be discussing one particular application of this point updates and range queries. And then I will give you 6 to 7 different practice problems that you can try out, and that would be an application of the problem that we will discuss in this particular video. So with that, let's get started. Firstly, we will look at the practice problem that we have that we will be asked to solve in the previous video. So we are given an array of size n, and there are two queries. The first query is of the form QLR. Basically, it needs us to print the minimum in the subarray L to R. And second query is UXY, which denotes that you need to update the value of index X to Y, right? Now, point updates and range queries. That's what you need to do in short. Now, this is the driver code. This is very simple. We are just taking in the inputs and the array. After that, we build the segment tree. So basically, this segment tree, I have created a class segment tree. We look at the class. Uh, the constructor of this class will actually build the segment tree. So we build the segment tree first, and then we will just input all the queries one by one. And if the query is of type QLR, we will simply call query on the segment tree. Otherwise, we will just call update on the segment tree. Now, this -1 are just to make sure that's just to tackle the one based indexing here. So the problem states that L and R would be one, basically would start with one. Basically, they will be one based indexed, but our array is zero based index. So that's where this -1 would help mitigate that. So this is the overall structure of the segment tree class. So it has constructor and two methods, query and update. Now constructor basically takes in an array and an integer n, and call build on this call build function, which is another private function of this segment tree class. So we are building the segment tree in the constructor, and these two queries are just calling internal query methods. So this update is also calling internal update method. Now, why we have modeled it this way? Because if you remember from the previous discussion, Let me just show you the pseudocode. So this was the pseudocode that we have discussed in the previous video. So everywhere we have three indexes, LRI, LRI, and LRI, right? And these three indexes are something which are internal to the implementation. Basically, when we need to query some range L and R or X or Y, we don't need to worry about this particular L and R. Like X and Y is completely separate of this L and R. So this L and R will just denotes the range of the current node. So just to recap this particular part a bit, what like how segment tree is built, each array index I would correspond to one leaf node of this tree, and each non-leaf node would just correspond to some function of left and right child, right? So in this particular case we have to find minimum of a particular range. So the non-leaf node would just denote the minimum of left and right child. So minimum of 3 and 1 1, minimum of 6 and 0 0, 4 and 8 minimum is 4, 5 and 2 minimum 2. Now 4 2 minimum is 2, 1 0 minimum is 0, and 0 2 minimum is 0. So that's how we build a segment tree. Now we also have discussed that we will not be using pointers to build this tree. Basically, will not use like any node and left and right pointers. Instead, we will be representing this entire tree in an array. And the index of left and right child would just be I cross 2 plus 1 and I cross 2 plus 2. So basically, we are representing this tree in an array. And if we are at node which is stored at index I, we will say that its left index would be stored at, sorry, if its left child would be stored at I cross 2 plus 1, and its right child would be stored as I cross 2 plus 2, right? So that's how we are uh, building, like we are storing the segment tree, right? So if you have any doubts in this until now, I would strongly encourage you to watch the previous video, because there we have discussed this particular thing in much more depth. So what we are doing, we simply call internal query method. This x and y we got from outside. Now we just pass in this x and y, and we are passing in 0 and n minus 1 and 0. Now if you look at the pseudocode, this needs L, R, and I. So we will always start with root. So root would corresponds to the range 0 to n minus 1, and the value of I for the root would be 0, right? We have discussed that. So that's what we are doing. Like we are calling internal query with 0 and n minus 1, and I is 0. Similarly for update, we are doing the same thing. The root node would be stored at 0, and L and R would be 0 and n minus 1, right? Now these are the three main functions. Now first build, if you remember how to build a segment tree, we said that okay, this building segment tree is a recursive process. We will, if we need to build a segment tree for the range 0 to 7, we will build the segment tree for the range 0 to 3 first. We will build the segment tree for the range 4 to 7 next. And finally, we will just merge uh, the root of these left and right, right? So that's what we are doing. We are checking, this is a base condition. Basically, if we reach at the root, if we reach at the leaf, leaf would have, leaf would correspond to one particular index of this array, right? So at leaf, the value of L and R would be same. So that's the base condition. L and R is same. We just assign the particular array element at that particular index in the tree. And after that, we just call build on the left. We just build the left half of the array, left half of the segment tree. We build the right half of the segment tree, and then we just simply merge. So now merging here just means finding out the min of the left and the right child, right? Now once we have built the segment tree, the query part is also very similar. So if you remember, the query part was, if you have to query x and y, what you will do, you will just check whether x and y lies in this range or not, or completely overlaps with this range or not. If it doesn't overlap with this range, you will go left and right both side, right? So for example, let's say you have to query for 1 to 6. So 1 to 6 doesn't overlap with 0 to 7. So you will go on both side. You then 0 to 3. 0 to 3 also doesn't overlap with 1 to 6. So you will again go left and right side. So 0 to 1. 0 to 1 doesn't overlap with 1 to 6 again. You will go left and right side. Now left is 0 comma 0. 0 comma 0 completely lies outside of 1 comma 6. So you will just ignore this particular thing, right? And when you like, you will try the next particular choice that you have, which is like the right child of this one, which is 1. 1 comma 1. 1 comma 1 completely lies here. So this is one candidate to your answer, right? Now in the same fashion you will find out all candidates and simply find, like, merge all the candidates. Now merging will depend on problem to problem. In this particular problem we are asked to find the minimum, so we will just find the minimum among all the candidates. So that's what we are doing. We check if the range is completely outside of x and y. So x and y is something that we need to query for. So we'll check whether current node L and R lies completely outside. If it lies completely outside, we return a very huge value. So if you remember previously, we are finding out sum. In sum, we have returned 0, because what we want is, we want, whenever we merge something, that merging should, like, this value should not interfere with that particular merging. So in case of summation, we return 0 because we know 0 plus x is 0. Similarly, here we have to find minimum, right? So that's why we return very large value, which is infinity, let's say. So whenever you do minimum of something comma infinity, you will always get something, because infinity is always greater than the first value. So you will always get the first value, right? So that's how this 118 comes from. Now after that, this is the second case where this node completely overlaps. If it completely overlaps, we will not expand further, right? So we'll just simply return. So we returned the current value. Otherwise, we go in the left and right child. We'll query for the left, we'll query for the right, and merge them. Now merging here means finding minimum, but it can be anything. Now finally, update was also very simple. So let's say you have to update 2 comma 4, basically update index 2 with a value of 4. So what you will do, you will simply see where does 2 lies. So 2 lies in 0 comma 3 or 4 comma 7. You will see, okay, 2 lies in the in the left part, so you will go in the left. Now again, you will see whether where does 2 lies, left or right. 0 comma 1, no, 2 lies in the 2 comma 3, so you will go there. Again same question, you will go come here. Finally, you whenever you reach the leaf, you know that you are at the current node which you want to update. You will simply update its value and propagate to all the children. So now while going back, all these nodes will be affected. So minimum of 4 comma 0, it would be 0. In this particular case it would not change, but it might change in some cases, right? So that's what we are doing. We are This is a base case. Basically, when we reach the leaf node, we simply update that particular value. Otherwise, we look at whether the index that we want to update lies in the left half. If it is like, if it lies in the left half, we will go in the left half. Otherwise, we will go in the right half. And finally, because either left or right was updated, so it may happen that you are going in the left or the right. It doesn't matter which path you take, but one of these may have updated, right? Based on what the values here are. So currently it was 4, so 0 comma minimum of 0 comma 4 was 0, so it is not updated. But let's say it is minus 4. In that case, you will update this to minus 4 as well, right? So basically, whenever anything is updated, like whenever you are going left and right, one of this is updated. So this node can also be changed, like may also change. So that's why we are again merging left and right, just to ensure that this particular node value is correct after changing or after updating the particular index, right? So this is the entire code for build, query, and update. Again, if you have any doubts in this particular in any of these parts, I would encourage you to watch the previous video, because there we have explained this in much better depth. So with that, let's move to the main part of the video, which is we will be solving one interesting application of range queries and point updates, which is querying on a prefix of an array. Now, what does this statement means? We will come to that afterwards. For now, we have to solve a a simpler problem. The problem is find out the number of smallest elements in the right or in the left. For example, let's say you are given an array 10, 8, 3, 1, 6, 4, 2, 9, and for each index, you need to find out how many elements are there which are smaller than current element in the left of the array, right? So in this particular example, for 6, the answer would be 2 because number of elements which are less than 6 are 1 and 3. So there are two elements which are less than 3, so answer is 2. Similarly for 4, answer is 2 because again there are two elements which are less than 4 in the left. For 2, answer is 1 because there are two elements. So there is only one element which is 1, which is smaller than 2. And finally for 9, there are 6 elements which are smaller than 9. 1, 2, 3, 4, 5, 6, right? 10 is greater than 9, so all these elements are smaller than 9. Hence, for this particular index, answer is 6. So basically, you have to return this particular array, which where each index would denote how many elements are there which are smaller than the element at that particular index I, right? So hope the problem statement is clear. Now you can solve this problem very easily in order n square time, right? How? You will simply iterate over the prefix of the array for each index. So let's say you are trying to find the answer for index I. You will just iterate over the prefix of the array and find out how many elements are there which are smaller than 6, and that would be the answer for I. So you can do this for every index and you can solve this in order n square. But we want to solve this in order n log n, right? So if you haven't seen this problem before, or you haven't solved this in order n log n before, I strongly encourage you to pause the video and try to think one step forward at least, right? So what exactly do we want? So we at particular index I, let's say we have to find the answer for index I, where I currently corresponds to 6. So what exactly do you need? You need number of elements which are smaller than 6. Now for this particular thing, number of elements which are smaller than a particular element, you need to have all the left elements sorted, right? First of all, so let's say you have some data structure that will help you keeping all the elements in sorted fashion. So this is something that you have. Now what you want count of all the elements which are smaller than 6. So what you need to understand first is where does 6 lie here? So basically lower bound or upper bound, right? Anything between them. Now, as soon as you do lower bound upper bound, you will get to the index where 6 would belong to. And from that, you will need to find out how many elements are there which are before that index, right? So what you need in total, you need three things from your data structure. So you need your data structure to insert an element by keeping the order sorted, right? So you need your data structure to have uh, basically, let's say you figured out the answer for I. Now you are trying to figure out the answer for this particular index, right? So for this particular index, you have to consider ith index as well, right? Because this index, the I index, this particular I index comes before this index, right? So you will be inserting 6 in your data structure, right? So that's what the first operation that your data structure should be able to do. Second, as we have discussed, that data structure should be able to perform lower bound and upper bound. And finally, that data structure should be able to count all the elements or count the number of elements which are before or after a particular index x, right? So these are the three things that your data structure should need to perform, and all of these should be in order log n, right? Otherwise, there would not be any point, and order n square solution is something that you already have, right? So think about it. What is the data structure that you can use to solve these three things? The first two things you can easily do with the help of a set in C++, or basically with the help of a balanced binary search tree in a trivial manner, right? The last one is something that you can't do with the help of a set. Now, if you don't understand this particular statement, basically what does set denotes? So set is nothing but a balanced binary search tree. So the set would have something like this, right? Now let's say you have to count the number of elements which are before this node, right? So to count the number of elements which are before this node, you have to actually do, or you have to go left and right? Basically, you have to go one left, and going to the previous node is something which is not a order one operation in set. So in this case, let's say you have to, for example, you have to go to the next node of this particular node. So the next node of this particular node would be this node, right? Now, from here, you can't directly jump here. That's not how balanced binary search tree works. So you have to traverse all the way to up, and then you have to come here, right? Now, because this entire thing is a balanced BST, this entire operation would take order log n time. That's what we are guaranteed. So finding previous element or the next element would require order log n time. And to find out how many elements are there in the left or the right, you have to do I minus minus, and each I minus minus would require you order log n time. And that's where finding or counting the number of elements before x would take you order n log n time. Now, log n for each I minus minus, and I minus minus you will do for n number of times, right? So this this single operation in set would require n log n time, but we want the entire thing to work in on n log n. So clearly set would not work here. Now, if you are curious and if you know how to implement set or any balanced binary search tree like AVL tree or red black tree, you can very easily code this particular thing yourself. Like you can modify a small uh, you can modify the structure of the node in a very small fashion, and you can able to serve this particular queries in order log n time itself. Now that's a problem for another day, but that is something which is possible, and if you're interested, you can try that. So for now, set is something that is of no use for us, right? We need to do something better. So what exactly can we do? So whenever you have these three kind of these three operation, you can do one small or one smart thing which can give which will not require you to implement AVL tree or something of that sort. Like you don't need to implement those complex data structure by yourself. What is the trick? The trick is just sort the array, and if you sort the array, you will see that these two operations is something that you don't require at all. So for example, let's say you sorted the array. Now after sorting the array would look like 1 2 3 4 6 8 9 10, right? Now you will say each of these array elements are inactive, right? So currently like no one has anything, so all these elements are inactive. Now, as and when you are traversing in the right, you will simply activate them, right? So notice why this is helping us, or how this is helping us. Well, as soon as we sorted the array, we don't need to understand where a particular element x will belong to, or like how to maintain the order, because let's say we need to insert 10, so we already know that 10 would actually go to this particular position at the end, so we'll directly insert 10 at the last position, right? So that's where we are completely getting rid of first and second type of query. Now what we are left of, we are now only left with the query where we need to count the number of elements which are before a particular index x, right? So let's take this example. Let's say you are like your I is at 10. So what does mean? It means that find me all the elements which are smaller than 10 uh, in the left of I. So left of I denotes this particular range, right? Now in this range, what you want how many elements are there which are which are present in the left, right? So basically, you as and when you will be visiting an element, you will mark it as one, otherwise it is zero. So currently everything here is zero. So it means nothing is present which is less than 10. So the answer for this particular index would be zero, right? So let's just move forward. Let's say this is I. Now before moving to this, you have to activate 10, because now 10 is something that you will be contributing to the next set of elements. So basically you will say 10 is activated, right? Now after that you will increment I. Now you have to find all the elements which are smaller than 8 in the left, right? So in the left, these are the elements which are present in the left, right, of 8. And you need to understand how many of them are smaller. So basically you just need to understand how many are ones. So there are no one, like no one of these indexes are one. So this again, the value here would be, answer here would be zero. Like there is no index which is smaller than 8 in the left. So for 3, again before going to 3 you will activate 8. So where does 8 belongs? 8 belongs to this particular index, right? So we will activate this particular index. Now same thing we will do for 3. So again you will not find anything and you will activate 3 at the end. And finally, for 1 you will do the same thing. You will activate 1. You will not find anything in the left, because left of 1 denote this particular piece. Basically there is no element at all, so there is no point of anything being active. Now let's take 6. So this is interesting. So 6 is this particular index. So you want number of elements less than 6. So these are all the elements which are less than 6. Now you actually want how many elements are actually present in the left. So these are all the elements less than 6, right? But you want how many are present in the left. And 2 are present in the left. Why? Because 2 are active, right? Hence the answer for 6 would be 2, right? So hope you got the intuition. What we are doing is we just sorted the array and we predetermined what would be the index of a particular element. After doing that, we simply iterate from left to right, and to query to find out how many elements are there which are less than 10. We already know that all the elements in this range would be less than 10. So what we just need to know that how many are present in the left, or in other words how many are activated. So what we can do, we can simply do a sum query in this range. So what we are doing in total, we are activating indexes one by one. So this is point updates. We are changing a particular index to 1. And second query that we are doing is we are querying a range L to R, right? So for 10, L to R would be L to R would be this. For 6, L would be at 1 and R would be at 4, right? And so on and so forth. So basically, we are doing point updates and range queries, and both of these can be done very easily with the help of segment tree. And hence, for each index, we can determine the answer in order login time, right? So let's just iterate through a example that would make things much more clear. So we have to count the number of elements in the left. So what we will do, we will simply build a segment tree where everything is 0 initially. Now everything is 0 and we are maintaining, we want to find the sum in a range, right? So basically each of these values would be 0 as well, because this would be the sum, a function of left and right, and function here is sum. We want to find the sum. So each of these index would be 0, right? Now after that, as we have discussed, what we will do, we will simply iterate over the array from left to right, right? So we are currently at index 1. Now For this particular index, we will look at, okay, this index maps to index number 7, right? So what we need to know is how many elements are active in this range. So we'll just simply do a range query in the range 0 to 6, right? Now, why 0 to 6? 0 because this is the first, like this L would always be the first index because we want to consider everything in the left, right? And 6 because uh, 10 maps to 7, seventh index, right? 10 maps to 7 index. And we know that everything, because the array is sorted in this particular fashion, we know that everything before 7 would be smaller than 10, and that's why we are querying in the range 0 to 6. So if you query the range 0 to 6 in this segment tree, you will get 0. So that's why answer here is 0, right? Sorry, answer for this particular position would be 0. Now you will say, let's try out this particular position I. Now before moving to this particular position I, we have to activate this index because now 10 is activated, right? So we will just activate 10. Basically it means you are updating this particular index value to 1. So what you will do, you will simply remove this 0 and update it to 1. Similarly, you will remove this. This will be updated to 1. Why? Because 0 plus 1, 1. Similarly, this would be 1 and this would also be 1, right? And now for 8, again, you will do the same thing. You will see, okay, 8 is mapped to this particular index, which is 5. So you will simply do a range query in the range 0 to 4, and again you will get 0. So the answer for this particular index would be 0. And after getting the answer, you will also activate 8 because now 8 would be contributing to next set of indexes. So activating 8 would mean that you have to set the index 5 to 1. So as you will set the index 5 to 1, it would be 1. It would be 1. Now this would be 2 because 1 plus 1 would be 2, right? And this would also be 2 because 0 plus 2 would be 2. And same you will do for 3, right? And so on and so forth. So hope you got the intuition. So how to code this? Coding, it will be very very straightforward. We already know how to code segment tree. We have looked at this particular thing. Only thing here that would change is this merge function. So here we were using minimum to merge the function because we have to we have been asked to find the minimum in the range, but in this particular problem we have to sum a particular range. So this function would just change to addition, right? So just to show you one particular code, so this would be the code for that particular sum segment tree. Only thing you can see here changed is this minimum here changed to addition. The return in case of non-overlapping was previously 10 to the power 18, right? Because we want to make sure that this return doesn't overlap with the or doesn't pollute original answer. And because it was min, we choose int maximum or 10 to the power 18, which can be maximum in that particular problem. But here it is sum, so that's why we choose 0 because we know 0 plus x would be x. Basically whatever sum that we would be getting, that would not be polluted with this 0 at all, right? And finally with update as well, only thing that change here is this particular thing, right? So now I would encourage you to solve this particular problem 57e of code forces. This is a fairly hard problem, but all you need to do here is simply calculate the exact same thing, like number of elements in the left, number of elements smaller than the current element in the left. So you can try, like this is little bit more than finding number of smaller elements in the left, but uh, converting this problem to this problem would just be a simple step away, and we have discussed that step multiple times in this particular channel. So I would encourage you to solve this particular problem first by yourself, and there are multiple different problems that I have shortlisted. So if you are still not sure about your segment tree code, or if you're still not sure that you're not able to code segment trees well, then I would recommend solving this particular problem first. Otherwise, if you understand how to code segment trees in a fair manner, I would encourage you to start with this enemy is weak that I just shown here, and then you can try these all problems. So what we'll be doing from now on, I will be trying to solve each of these problems in in the coming up videos. So stay tuned for that. And if you like the video, give it a thumbs up and do subscribe if you haven't already, so that you will not miss any of these updates. So with that, hope you enjoy it, and I will see you in the next one. Thank you.